Hi everyone, welcome to Expressive Developer Conference 2024. The topic of this session is about USB. Let's start to explore the USB capabilities of ESP chips. This session will cover the following topic. First, I will talk about the USB basic concepts. Then I will talk the USB supported in ESP chips. Then the USB host development guide, USB device development guide, and finally talk about the ESP-related solutions. So first, let me introduce myself. My name is Li Bo. I am the engineering manager from application team. In the past few years, our team has been working on the USB developing for ESP chips, provide various USB solutions for our customers, and support our customers to make competitive products. And I'm also the maintainer of the ESP IoT solution repository. Okay, let's go to the first part, the USB basic concept. So first, imagine a world without USB, various devices from different vendors using different interfaces or even different protocols. You have to carry a lot of cables, adapters, and it's not possible for manufacturers to make portable product with so many ports. So USB is born to solve these problems. It makes our life easier. USB full name, Universal Serial Bus, and it is defined by the USB implementers forms. The specification defines not only the communication protocol, but also the physical interface and the power supply. So it makes it easier for the device with USB interface to connect to each other. Many types of USB devices around us, such as a mouse, a speaker, camera, USB disk, and the gamepad. Now, USB chips with USB support can join the big family. You can develop all the mentioned devices in the picture with ESP chips. And furthermore, you can also develop USB hosted devices, and the device can connect to these devices like what PC do. So you may have a question now how this device works, why they can know each other, and how did they communicate with each other. So first, let's take a look at the USB bus. In the USB system, there are different rows of USB devices, the USB host and the USB device, and there are also special devices like USB hub. The USB hub can connect to multiple devices in the downstream. So finally, the USB bus seems like a tree structure. And please keep in mind the USB communication is always initiated from the host to device. USB-IF also defined many device classes. Device classes specification like HID for the mouse and game port, and the MSC mass storage classes for the USB flash drive, and the UAC for the web camera, UAC for the USB speaker, USB microphone, and the descriptor. We may have heard the descriptor. The descriptor is the structure that contains the information about the device types and the capability, which is fetched from the host during the enumeration process. So when a device is connected to the USB system, the host will first enable the device, get the descriptor, and give an address to the device. The address is used for the further communication. And the data transfer always happens from endpoint to endpoint. The packet is the minimum unit of data. There are three types of package: the token package, the data package, and handshake package. The token package usually contains the target device address and the endpoint address. It makes the target device know which packet is sent to itself. And the transaction is a fully complete data exchange, which contains a token package, data package, and handshake. Transfer contains multiple transactions, like you want to fetch an image from a UVC camera. One transfer may be to get one frame, but during the one frame, many transactions will be sent. Except for the transfer format, the USB also defines different transfer modes to meet the different requirements of application scenarios, like the control transfer for the device management, the interrupt transfer for the periodic data report, and the bulk transfer for the large data transfer, like we use the USB disk for the files copy. And asynchronous transfer for the real-time data transfer, like we use the UVC for the pictures. Okay, let's move on to the second part, the USB support on USB chips. Expressive has developed a series of chips with USB support from the ESP-32S2 to the ESP-32P4. Like ESP-32S2, ESP-32S3, and the ESP-32P4, they all have USB-OTG support. But for the chip ESP-32C3 and the C6, they only have USB-Serial-JTAG. So what's the difference between the USB-OTG and the USB-Serial-JTAG? First, let's talk about the USB-Serial-JTAG. USB-Serial-JTAG is designed to replace the external JTAG adapter or USB to UART bridge used to provide more direct way to debug and download through a simple USB cable. It's a dedicated USB device with hard-coded descriptors, which means you cannot change the descriptors and functions. The chip with USB-Serial-JTAG supports two interfaces, the USB to JTAG interface and the USB to serial interface. The USB to JTAG interface is used for JTAG debugging, and the USB to serial function is used for the firmware download, log, and the user communication. You can also control the device to enter into the download mode by using USB CDC request, like set line state command. You can use the ESP2 to directly change the chip to download mode through the USB command. If you want to know the details about what it happened, please refer the technical reference manual of this chip. So if you want to develop a USB device or USB host with more features, please select the chips with USB-OTG support. The S3 supports USB-OTG full speed, and the P4 supports USB-OTG high speed. For the chips with USB-OTG full speed support, it usually have an embedded USB PHY, or you can call it USB transceiver. The clock speed is 12 megabits, but the actual data rate depends on the device classes and depends on the transfer modes I mentioned. Different device type of devices may use different transfer modes. The maximum data rate for user data would be around 8 megabits due to the protocol overhead, but it's already enough for most USB devices like USB mouse keyboards and some audio device or even some lower resolution cameras. The controller supports USB host and device functions and OTG functions. You can choose the mode by initialize different USB stack. For host mode, you can have 7 configurable endpoints. For device mode, you have 6. The endpoint number means how many endpoints you can use for the data transfer at the same time. For example, if you work on the host mode, you have 7 endpoints, which allow you to connect to CDC ACM devices at the same time, because each CDC ACM interface consumes 3 endpoints. So you have 7 endpoints. You can connect to 2 such devices and 1 endpoint left for other devices. Dynamic FIFO is used for the buffer the date during the date transfer. All endpoints show 1 kilobytes FIFO. It means you cannot choose endpoints with larger maximum package size than 1 kilo. It's a limitation for some UVC devices. Compared with the USB full speed, the USB-OTG high speed has a higher clock speed and the large FIFO. You have 4 KB resource and a more configurable endpoint. That means you can connect it to more devices at the same time. You can have the better support of the USB hub. S3 is a special keep because you have both the USB-OTG and the USB-Serial-JTAG controller. They share the same internal USB PHY. By default, the internal USB PHY is connected to the USB-Serial-JTAG, which means you can use the USB-Serial-JTAG function directly for firmware download log without any configuration, without any code. If you want to use the USB-OTG function, you need to initialize the USB-OTG stack. The USB PHY will be switched to the USB-OTG internally during the stack start. And after the USB-OTG occupies the internal PHY, the USB-Serial-JTAG will be disabled. So if you want to use the USB-OTG and the USB-Serial-JTAG at the same time, you can choose to add an external PHY, add another external PHY to make it work at the same time. But if you select P4, you can use the USB-OTG high speed, full speed, and the USB-Serial-JTAG function at the same time, because each controller has its own PHY. Okay, let's move on the development part. First, let's talk about the USB host stack and the host classes. This is a USB host driver stack in ESP-IDF, which is divided into several layers from the bottom LL layer to the top class driver layer. For most users, you only need to focus on the class driver layer because it provides a set of APIs to control your device and transfer data. Take the UVC class driver as an example. It provides APIs to mute audio device, set volume of the audio device, and it also provides APIs for you to read and write data. The class drivers currently supported by ESP-IDF are HID, CDC-ASM, the MSC, UVC, and UAC. Based on these class drivers, you don't need to care about how the USB host library works, or even you don't need to know which specified USB endpoint is used for the data transfer. So let's take this project as example. The project is to add USB headphone support for ESP32S3 box 3. The USB box has a built-in speaker, but the sound quality is not very good. So imagine if you want to add a headphone support, how to achieve it. Yes, the answer is using USB host interface. If we develop based on the UAC class driver, we don't need to care about the USB details. Key process, let's dig into the key process. So first step, you only need to open a specific device with a USB host device open, because in your USB system, you may connect to two devices, or the devices may have two interfaces, like one interface for microphone, one interface for the speaker. So you need to first choose which one you want to open. So in this step, we open the speaker interface. Then we can start a speaker stream using the specified audio format. Like you need to configure the channels, the sample rate, the bit resolution, and the other audio configurations. With the USB hosted device start, a stream will be started in background. Then you can call the write data API, like you UEC hosted device write, to write the data to the internal buffer. The internal buffer will finally send the data to the USB LAN with the USB in idle state. So if you develop the project based on the class drivers, you should have hear the music from the headphones. Furthermore, if you want to control the volume, you can call the USB hosted device set volume to control the voice volume. And if you want to make your project more robust, you need to handle the connect and disconnect callback, because the USB headphone may be disconnected in any time. So you need to pause the playback when the device is disconnected, and resume the playback when the device is replugged in. And we already have examples in the ESP box repo. You can refer the link for the details. And if the class driver you want to use is not currently supported by ESP-IDF, especially for some vendor-specified devices, you may need to develop your own class drivers based on the USB hosted driver, which may not difficult as you think, because the USB hosted driver internally handles the USB connection and the disconnection, and also enumerates the devices, set the device address and the cache device descriptors in RAM. You can fetch your descriptors in any time. And the USB hosted library also provides a set of APIs to control the device, and provide API to transfer data also. You only need to focus on the specific device communication protocols and implement the APIs. So let's take this project as an example. So here we want to add the support for a vendor-specified USB device. So let's assume the device has multiple interfaces, and each interface have two bulk endpoints, one for read, one for write. So first step, you need to register your driver to the USB host driver, to the USB host library, to get informed when a new device is connected. If you're not registered, no inform for the new device. And after the USB device connected, you can read the device's descriptors with another API. You can check the device's ID, PID, and other information to make sure it's the device you want to operate. And for the vendor-specified USB devices, you should be clear which interface you want to communicate with. You can double-check the information with the vendor provider. Then you can claim the interface with the USB host interface claim. The claim interface means you open an endpoint. So after you end the point, you can prepare and submit the transfer to the endpoint using the USB host transfer submit. So each transfer will have a callback function. After the transfer completes, the transfer callback will be called. So in the callback function, you can pass in the data and schedule the next transfer if you need. Like the UVC, when you pass in a callback, then you need to schedule another one for the next frame. Okay, let's go into the USB device development. For the USB device stack, we directly using the TinyUSB. The TinyUSB is a well-known USB stack designed for microcontrollers. Expressive has ported it to ESP32S and P-series chips. TinyUSB itself supports both host and the device stack, but we only use the device stack in our chips. The support of the USB device mode is provided by the DCD port level implement. The DCD ESP-32 provide some necessary functions like DCD endpoint open to config endpoint, and DCD endpoint transfer for the endpoint data transfer, and other functions for the bus configuration, bus reset, and other things. If you search the ESP registry, you can find many TinyUSB related components maintained by Expressive or maintained by individuals. But the base component is Expressive TinyUSB. This component wraps the original repository as a ESP IDF component, which will be built as a static library, provides the core USB stack and the device driver from the TinyUSB. The ESP TinyUSB component is based on the Expressive TinyUSB, and it provides more easier to use APIs for the users. And it also supports config the device information, config which class you want to enable through the kconfig. And they also add some ring buffer to buffer some data for the users. And based on the ESP TinyUSB, there are also other specified function components like USB device UAC, especially for the UAC device, and the UVC especially for the UVC device. Let's take USB flash disk as an example. I will explain how to use it easily, write a simple code with the help of the ESP TinyUSB component. So here I use a USB-OTG developer board to simulate a USB disk. So the only thing you need to know is first to prepare your storage media. Like you need to choose where the data should be stored. Like you can choose a flash, internal flash, or the external SD card. You can directly call the wrapper function TinyUSB MSC storage init to init the file system. And then you can enable the MSC classes through the miniconfig by default. I think by default, MSC class is not enabled, so you need to enable it. The third step is just install the driver using the TinyUSB driver install. After you install, background tasks will be running. So after the three steps, you can connect to your ESP32 or other chips to the PC. The USB flash disk will be mounted to the system. You can find the new drive in the system. But until now, not all the classes supported by TinyUSB also supported by ESP TinyUSB. If you want to use that classes, like if you want to use the audio, the UAC class from the TinyUSB, you need to implement yourself. You need to implement some necessary callback based on the TinyUSB APIs. I will take this one as an example. If you want to build your ESP box as a USB speaker, you need the following key process. So first, you need to provide a TUSB config.h file with the config audio enabled to 1. The whole file you need to provide. You can also just copy paste from other project and modify the corresponding configurations manually. Second, you need to implement the necessary callbacks for the audio function. Like for the descriptors, you need to implement your device descriptors and the configuration descriptors and others. Then you tell your descriptors through their two callbacks. And you also need to implement some callbacks about the data receiving for the USB speaker. By implement the RX down post rate, you can get informed after each transfer. In the transfer complete callback, you can pass in the data. You may can store it in a rebuffer, and then you schedule the next transfer. If you want to provide much more functions, you need to implement other callbacks, but not all the callbacks are necessary. If you want to check more details, you can also look into the ESP box repository. We have an example there called the USB headset. Okay, the last part is about USB applications. I will introduce some USB applications or solutions based on the USB chips developed by the application team. The first one is USB multimedia solutions, which is designed for the S3 and the P4 chips. It supports UVC 1.5, UVC 1.0 standard. And using these chips, you can also add a local display. With the Wi-Fi support, you can also support Wi-Fi streaming to the portable devices. And for the performance, currently for the S3, we can achieve 15 frames per second for 400 resolution, and we can have 1000 resolution at the 30 frames for the ESP32P4. And with the help of the hardware JTAG decoder in the P4, you can achieve 700p 30 FPS using the ESP32P4. This solution is suitable for the smart doorbell and endoscope cameras and other related scenarios. The second one is USB external storage solutions. Also for the S3 and P series chips, they follow the MSC standard, support the file system, and support hot plug. For the performance, we support 32 gigabyte storage by default. If you want to support here storage, you need to modify the file system to enable EX5 file system. For the test results in the ESP32 S3, we can achieve 800 kilobytes per second. For the P4, we can achieve 12 megabytes per second. So for the application scenarios, it's suitable for the multimedia player and the AD screens. The third one is communication solutions. Because with the help of the ESP modem component, we can support the standard PPP protocol, and with the ability of Wi-Fi, we can also start a Wi-Fi hotspot to share the internet to other devices. With the 4G Cat 1 module, we can achieve 6 megabits per second for the download and 4 megabits for the upload. This application is suitable for the IoT gateway and the MiFi for the mobile phones. If you want to find more USB-related solutions or other solutions, or if you want to find our support, you can directly go to our official website. We have a USB solution page, there are more solutions here. And for the resources of this topic, you can manually check the 3 repository. Okay, I think that's all. Thanks for watching.